Hello, in this lecture we'll find out the area of the big rectangle EAFG. In the drawing we have the big rectangle EAFG. Inside this big rectangle we have this small circle. The radius of this small circle equals to 5 units now. This is the medium circle. The radius of this medium circle is equal to 6 units now. And this is the big circle. The radius of this big circle equals to 8 units now. Again, our task is to find out the area of this big rectangle EAFG. So first of all, we know that all the angles inside the rectangle are right angles. So actually, this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. The radius QB of this medium circle is drawn to point B, that is the point of tendency of tangent FG with this small circle. And whenever your radius is drawn to the point of tendency, then tangent FG will be perpendicular to the radius BO. If FG is perpendicular to BO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, the radius PA is equals to 5. The radius PA is drawn to point A, that is the point of tendency of tangent EA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius AP. If AE is perpendicular to AP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. Likewise, the radius SC of this big circle, the radius SC is equals to 8. The radius SC is drawn to point C, that is the point of tendency of tangent EA with this circle. And now you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius CS. If AE is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. We define the point of tendency of tangent AG with this big circle. This point is point T. We join points S and T together by a straight line. ST is of course the radius of this circle, that is equal to 8. The radius ST is drawn to point T, that is the point of tendency of tangent AG with this big circle. Whenever your radius is drawn to the point of tendency, then tangent AG will be perpendicular to the radius ST. If AG is perpendicular to ST, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in quadrilateral CATS, inside this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth angle must be equal to 90 degrees in its size. We define the point of tendency of tangent FG with this big circle. This point is point X. And we join points S and X together by a straight line. SX is of course the radius of this circle, that is equal to 8. The radius SX is equal to 8 is drawn to point X, that is the point of tendency of tangent FG with this big circle. And whenever your radius is 1 to the point of tendency, then tangent FG will be perpendicular to the radius XS. If HD is perpendicular to XS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So inside the small quadrilateral STGX, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 450 degrees. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 450 degrees must be equal to 90 degrees in its size. Angle CSX, the big angle CSX is equal to 90 degrees plus 90 degrees, that is 180 degrees. So written on, angle CSX equals to 180 degrees in its size. And we know that any angle that is equals to 90 degrees in its size, any angle that is equals to 180 degrees in its size, like this angle CSX, it is defined as a straight line. So line segment CSX is a straight line. Line segment CSX is a straight line. If line segment CSX is a straight line, then CX is also a straight line. CX is a straight line. If CX is a straight line, it means that this shape ECXF, this big shape ECXF has 4 sides, and therefore shape ECXF is a quadrilateral. So shape ECXF is a quadrilateral with 4 right angles, and therefore quadrilateral ECXF, this big quadrilateral, is a rectangle. Okay. So you know, the big quadrilateral ECXF is a rectangle. ECXF, quadrilateral ECXF is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECXF, in this big rectangle, side CX must be equal to side EF. But CX in total is equal to 8 plus 8, that is 16. Therefore, the opposite side EF must be also equal to 16 units in its length. So EF equals to 16 units in its length. EF, actually it is the width of rectangle EAFG. So we found out that the width of rectangle EAFG is 16. We have to find out the length of the rectangle, and the width times the length is the area of rectangle EAFG. So the width of rectangle EAFG, the width EF is 16. In the next step, we'll join points P and this point. We define the point of tendency of tangent EF with this small circle. This point is point L, and we join points P and L together by a straight line. PL is of course the radius of this small circle, that is equal to 5. The radius PL is drawn to point L, that is the point of tendency of tangent EF with this small circle, and whenever your radius is drawn to the point of tendency, then tangent EF will be perpendicular to the radius LP. If AF is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral, small quadrilateral AELP, we have 1, 2, 3 angles. The fourth angle must be equal to 90 degrees. So quadrilateral EAPL is point angles, and therefore quadrilateral EAPL is right angle, and in order the opposite sides of right angle are equal to each other. So the small right angle EAPL side LP must be equal to the opposite side EA, but LP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step, we'll join points P and Q together by straight line. That is to say, we'll join the center of the small circle with the center of the medium circle by straight line. And we'll define the touching point of the small circle with the medium circle. This point is point K. Here we can implement rule 10 because we have an external half between the medium circle and this small circle. That is to say, they touch each other externally at point K. So we can implement rule 10. According to rule 10, if two circles touch each other externally, those two circles touch each other externally at point K. Then the straight line that connects their centers together passes through their touching point. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects their centers together, is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point K, that is their touching point. Again, the straight line OM must pass through their touching point, that is point K. Or OKM is one straight line. Again, OKM is one straight line. So we can implement rule 10 in our drawing, because in our drawing we have an external between the medium circle and the small circle. That is to say, that touch each other externally at point K. So according to rule 10, the straight line PQ must pass through point K, that is their touching point, or PKQ is one straight line. PKQ is one straight line. PK is the radius of this circle, that is 5. QK is the radius of this medium circle, that is 6. And because of the fact that PKQ is one straight line according to rule 10, therefore PQ must be equal to 5 plus 6, that is 11. So in total, PQ equals to 11 units in its length. PQ equals to 11 units in its length. In the next step, we will draw from point Q, we draw perpendicular on EA. Again, from point Q, we draw perpendicular on EA. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and EA. This point is point Y. In the next step, from point P, we draw perpendicular on YB. Again, from point P, we draw perpendicular on YB. So actually, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and YB. This point is point S. So inside quadrilateral AYSP, we have 1, 2, 3 angles, and therefore the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral AYPA is a rectangle. So it is on. This is quadrilateral AYSP. This is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AYSP, side AB must be equal to the opposite side YS, but AP is 5, therefore the opposite side YS must be also equal to 5 units in its length. From point Q, we will draw perpendicular on EF. Again, from point Q, we will draw perpendicular on EF. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and EF. This point is point Z. So inside quadrilateral QZF, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees. Inside quadrilateral SLZQ, we have 1, 2, 3 right angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size. So actually, this is angle YSB, is equal to 180 degrees in its size, and therefore YSQ is a straight line. This is angle SQB, that is also equals to 180 degrees in its size, and therefore line segment SQB is also a straight line, and therefore in total we actually found out that YB is one straight line. Again, YB is one straight line, and therefore shape EYBF, this shape EYBF has 4 sides. 1, 2, 3, 4, and therefore shape EYBF is a rectangle, is a quadrilateral. Shape EYBF is a quadrilateral because it has 4 sides. In quadrilateral EYBF we have 1, 2, 3, 4 right angles, and therefore quadrilateral EYBF is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. In the big rectangle EYBF, side EF must be equal to the opposite side YB. But EF is 16, therefore YB must be also equal to 16 units in its length. So YB is 16, and therefore this missing 97SQ must be equal to YB, that is 16, minus 5 minus 6. Again, YB, that is 16, minus YS, minus QB is equal to SQ. So in total, the missing 97SQ must be equal to YB, that is 16, minus YS, that is 5, minus QB, that is 6. So in total, QS must be equal to 16 minus 11, that is 5. So the missing 97 QS must be equal to 5 units in its length. In the next step, we'll implement the Pythagoras theorem on this green right angle, PSQ. So we copy the right angle PSQ in the new page, and we'll implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evolution from Pythagoras theorem. So actually, this is the right range triangle PSQ that is coming from the original drawing. And this right triangle PSQ according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, equals to PS squared plus SQ squared. So write it down. PQ squared, that is the square of the hypotenuse, equals to PS squared plus SQ squared. PQ is 11, therefore PQ squared is 11 squared, that is 121, and it is equals to PS squared. PS is the missing side, so leave it as it is. So it is PS squared plus SQ squared. SQ is 5, therefore SQ squared is 5 squared, that is 25. In total, we should find out that 121 equals to PS squared plus 25. Here we will subtract 25 from this equation, and we get that 121 minus 25 is 96, equals to PS squared. PS squared equals to 96. Here we take a root out of this equation, and we get that PS equals to the square root of 96. 96 is 16 times 6. So we substitute 96 by 16 times 6. The square root of 16 is 4. So this expression in total will be equal to 4 times square root of 6. So we found out that the length of the missing line segment PS is equal to 4 times square root of 6 units in its length. PS equals to 4 times square root of 6 units in its length. This is the missing line segment PS. This is equals to 4 times square root of 6 units in its length. So I don't know. We have already found out that AYSP is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. So in a rectangle AYSP, side PS must be equal to the opposite side YA, but PS is 4 times square root of 6, therefore AY must be also equal to 4 times square root of 6 units in its length. In the next step, we'll join the center of this big circle, that is point S, with the center of this medium circle, that is Q. So we join points S and Q together by a straight line. Here we can implement rule 10. Whenever you have an external notch between two circles, the straight line that connects their centers, that is actually SQ, must pass through their touching point. We define their touching point as point L. According to rule 10, SLQ is one straight line. SLQ is one straight line. QL is the radius of the medium circle, that is 6. SL is the radius of this big circle, that is 8. Because of the fact that SLQ is one straight line, it means that SQ must be equal to 8 plus 6, that is 14. So SQ equals to 14 units in its length, according to rule 10, of course. From point Q, that is the center of this medium circle, we'll draw perpendicular on CX. And then from point Q, we'll draw perpendicular on CX. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point Q and CX. This point is point D. By doing this construction, we can get the lower quadrilateral QBXD. Inside this lower quadrilateral QBXD, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral QDXB, we have 4 right angles, and therefore quadrilateral QBDX is a rectangle because it has 4 right angles. Right now. But we also know that the opposite sides of a rectangle are equal to each other. So in this lower rectangle QBDX, side QB must be equal to the opposite side DX. But QB is 6, therefore the opposite side DX must be also equal to 6 units in its length. So writing on, dx equals to 6 units in its length. Sx, this is line segment Sx, it is the radius of the big circle, that is 8. Therefore, the short line segment SD is equal to Sx minus dx. Again, Sx minus dx equals to this short line segment SD. So at the end, we should find out that SD equals to Sx minus dx. So SD in total equals to Sx is the radius of the big circle, that is 8, minus dx. We just write and found out that dx equals to 6. So in total, SD equals to 8 minus 6, that is 2. So it is known SD equals to 2 units in its length. This is the short line segment SD. This equals to 2 units in its length. In the next step, I'll copy the green right triangle QSD in a new page, and we will implement on this green right triangle QSD the Pythagoras theorem. QD is actually the missing side. We just right now found out that ds equals to 2 units in its length. And the hypotenuse SQ equals to 14 units in its length. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QSD, that according to the original drawing. In this right triangle QSD, according to the Pythagoras theorem, SD squared SQ squared, that is the square of the hypotenuse, equals to SD squared plus QD squared. So I write it down. SQ squared, that is the square of the hypotenuse, equals to SD squared plus QD squared. The hypotenuse SQ is 14, therefore SQ squared is 14 squared, that is 196. And it is equals to SD squared. SD is 2, therefore SD squared is 2 squared, that is 4, plus QD squared. QD is the missing side, so we leave it as it is. So in total, we actually found out that 196 equals to 4 plus qd squared. Here we subtract 4 from this equation, and we get that qd squared equals to 196 minus 4 is 192. 192 is 64 times 3. So we substitute 192 by 64 times 3. So qd squared equals to 64 times 3. Here we take a root out of this equation, and finally we get that qd equals to the square root of 64, that is 8, times square root of 3. So in total we found out that the missing side qd equals to 8 times square root of 3 units in its length. This is the missing 97 qd, that is equals to 8 times square root of 3 units in its length. This is quadrilateral YQSD, inside YQSC, inside this quadrilateral YQDS. This is quadrilateral YQDC. Inside this quadrilateral YQDC, we have actually we have 1, 2, and 3. We have 1, 2, 3 right angles. Again, in quadrilateral CDQY, we have 1, 2, 3 right angles. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrilateral YCDQ, we have 4 right angles, and therefore quadrilateral YCDQ is a left angle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle YCDQ, side QD must be equal to the opposite side YC, but QD is 8 times square root of 3, therefore the opposite side YC must be also equal to 8 times square root of 3 units in its length. In this quadrilateral ACST, this small quadrilateral, we have 4 right angles, and therefore this small quadrilateral is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ACST, side ST must be equal to the opposite side CA. But ST is 8, that is the radius of the big circle, this big circle, and therefore the opposite side CA must be also equal to 8 units in its length. So now we have the length of rectangle EAFG. The length of rectangle EAFG is equal to EA, that is 5, plus AY, that is 4 times square root of 6, plus YC, that is 8 times square root of 3, plus CA, that is 8. The length is the expression that I just right now talked about it, and this the width of rectangle EAFG is 16 units. So the width, that is 16, times the length, that the length is 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. In total, it is the area of rectangle EAFG, that is the area that we are looking for in this question. So repeat again, the area of the big rectangle EAFG of the big rectangle EAFG is equal to the length, the width times the length, the width times the length. The area of rectangle EAFG equals to the width times the length. the width is EF, and the length is EA. So EF times EA is the area of rectangle EAFG. EF, the width EF is 16, and the length EA, the length EA equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. So in total, the area of rectangle EAFG is equal to 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. Actually, in total, the value of this expression it is equal to 586.47 square units in its size. Repeat again, we should find out that the area that we are looking for in this question, that is the area of this big rectangle EAFG, total is equal to either 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8 square units in its size. So in terms of numbers, the area of this big rectangle EAFG is equal to 586.47 square units in its size. So we finished the rest of the question. So in the next step, I'll summarize the lecture. So in this lecture, our test was to find out the area of this big rectangle EAFG. Inside this big rectangle EAFG, we have 3 circles. This is the small circle with radius 5. This is the medium circle with radius 6. And this is the big circle with radius 8. Again, our test is to find out the area of this rectangle EAFG. First of all the sides, all the angles inside rectangle EAFG are right angles. Those 4 angles are all right angles. And we implemented here rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So PA is the radius of this small circle, that equals to 5. The radius PA, that equals to 5. The radius PA is drawn to point 8, that is the point of tendency of tangent EA with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent EA will be perpendicular to the radius AP. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, I'll not repeat on the same rule again. The radius SC is tangent to EA, tangent to the radius CS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. Likewise, those 2 angles are also right angles. Those 2 angles are also right angles according to the same rule, rule 1. We join points P and L together by straight line. PL is the radius of this small circle, that is equal to 5. And EF is the point of tendency of tangent. L is the point of tendency of tangent EF with this small circle. And therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside the small quadrilateral EAFL, we have 3 right angles. Therefore, this 4th missing angle must be equal to 90 degrees in size. Therefore, quadrilateral EAPL is at least a rectangle, if not a square. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle EAPL, LF side PL must be equal to the opposite side AE. But PL is 5, therefore the opposite side AE must be also equal to 5 units in its length. Likewise, we join points S and D together by a straight line. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the small quadrilateral STAC, we have 1, 2, 3 right angles, and therefore this fourth piece angle must be also equal to 90 degrees in its size. Therefore, quadrilateral STAC is a rectangle according to rule 5, and we know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AC ST, side ST must be equal to the opposite side ST. But ST is 8, therefore the opposite side AC must be also equal to 8 units in its length. So here, this angle equals to 90 degrees, and in quadrilateral STGX we have 1, 2, 3 right angles, and therefore this fourth piece angle must be also equal to 90 degrees in size. So angle CSX, this big angle is 90 degrees plus 90 degrees, that is 180 degrees, and therefore angle CSX equals to 180 degrees in its size, and therefore line segment CSX is a straight line. If line segment CSX is a straight line, then CX is also a straight line, and therefore shape CXFE, this big shape, has 4 sides, and therefore this shape is a quadrilateral because it has 4 sides. In quadrilateral ECXF we have 4 right angles, and therefore quadrilateral ECFX is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECXF, side CX must be equal to the opposite side EF. But CX is 8 plus X, that 8 plus 8, that is 16. Therefore the opposite side EF must be also equal to 16 units in its length. So if you found out that the width of the big rectangle EAGF is equal to 16 units. In the next step, we draw perpendicular from point Q to EA. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and EA. This point is point Y. And we also, from point P, we do perpendicular on YB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So in total, in the small quadrilateral AYSP, we have 1, 2, 3 right angles. And therefore, the fourth angle must be also equal to 90 degrees in size. So in this rectangle AYSP, side AP must be equal to the opposite side YS. But AP is 5, therefore the opposite side YS must be also equal to 5 units in its length. So here, we implemented the Pythagoras theorem on this right green triangle PSQ. The hypotenuse PQ is 11, it is 5 plus 6, that is 11, QS is 5, and PS is the missing side. So actually, I copied this green right triangle in an equation implemented on it the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the green right triangle PSQ that I copied from the original drawing. In this green right triangle PSQ, PQ squared, that is the square of the hypotenuse, equals to PS squared plus SQ squared. PQ is 11, therefore PQ squared is 11 squared, that is 121. And it is equals to PS squared. PS is the missing side, so leave it as it is, plus SQ squared. SQ is 5, therefore SQ squared is 5 squared, that is 25. So in total, we found out that 121 equals to PS squared plus 25. Here we subtracted 25 from this equation, and finally found out that 121 minus 25 is 96, so 96 equals to PS squared. Here we took a root out of this equation, and finally found out that PS equals to the square root of 96. 96 is 16 times 6, so we substitute 96 by 16 times 6, and finally found out that PS equals to the square root of 16 is 4 times square root of 6. So this is the missing side PS is equal to 4 times square root of 6 units in its length. So in rectangle AYSP, side PS must be equal to the opposite side AY, but PS is 4 times square root of 6, therefore the opposite side AY must be also equal to 4 times square root of 6 units in its length. In the next step, we join the center of this medium circle, that is point Q, with the center of this big circle, that is point S. That is to say, we join points S and Q together by straight line. Here, because of the fact that we have an external arc between the big circle and this medium circle, we can implement rule 10. According to rule 10, the straight line that connects their centers together, the straight line that connects the center of this big circle with this medium circle, the straight line AQ must pass through point L, that is their touching point. Again, the straight line SQ must pass through point L, that is their touching point. Or SLQ is one straight line. Again, SLQ is one straight line. QL is the radius of this medium circle, that is 6. SL is the radius of this big circle, that is 8. So in total, SLQ must be equal to SL plus LQ. Why? Because SLQ is one straight line. Therefore, SLQ equals to SL plus LQ. So SLQ equals to SL, that is L. SLQ equals to SL, that is 8, plus LQ, that is 6. So in total, SLQ equals to 8 plus 6, that is 14. So SQ equals to 14 units in its length. In the next step, from point Q, that is the center of this medium circle, we draw perpendicular on CX. And from point Q, we draw perpendicular on CX. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So inside the lower quadrilateral QSXB, we have 1, 2, 3 right angles. Again, inside this lower quadrilateral QDXB, we have 1, 2, 3 right angles. And therefore, this fourth missing angle must be also equal to 90 degrees inside, and therefore quadrilateral QBDX is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle QDXB, side QB must be equal to the opposite side DX. But QB is 6, therefore the opposite side DX must be also equal to 6 units in its length. SX, this is line segment SX, that is the radius of this big circle, that is equals to 8. DX equals to 6. So the small line segment SD equals to SX minus DX. Again, SX minus DX equals to this short line segment SD. So SD equals to SX minus DX. So SD, this short line segment SD equals to SX, that is 8, minus DX, that is 6. So in total, the short line segment SD equals to 8 minus 6, that is 2. SD equals to 2 units in its length, and the hypotenuse SQ of the green rectangle equals to 14 units in its length. So copy the right green triangle QSD in a new page, and we implemented the bottom also on this right green triangle QSD. So actually, this is the right green triangle QSD that comes from the original domain. This angle is of course the right angle. So in this right triangle QSD, according to the Pythagoras theorem, SQ squared, that is the square of the hypotenuse, equals to SD squared plus DQ squared. SQ is 14, therefore SQ squared is 14 squared, that is 196. And it is equals to SD squared. SD is 2, therefore SD squared is 2 squared, that is 4, plus QD squared. QD is the missing side, so we leave it as it is. So in total, we found out that 196 equals to 4 plus QD squared. If we substitute 4 for this equation, we found out that QD squared equals to 196 minus 4 is 192. So QD squared equals to 192. 192 is 16 times 4. So we substitute 194 by 64. Again, 192 is 64 times 3. we substituted 194 by 64 times 3, and we took a root from this equation, and I found out that QD equals to the square root of 64 is 8, so QD in total equals to 8 times square root of 3. So actually this is the missing side QD that is equal to 8 times square root of 3 units in its length. So in quadrigonal YQDC, this is the quadrigonal YQDC, we have 1, 2, 3 rectangles. Actually, in quadrigonal YCDQ we have 4 rectangles. Okay, again, in quadrigonal YCDQ we have 4 rectangles, and therefore quadrigonal YCDQ is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So in rectangle YCDQ, side QD must be equal to the opposite side YC, but QD is 8 times square root of 3, therefore the opposite side YC must be also equal to 8 times square root of 3 units in its length. Inside this one quadrigonal CATS, we have 4 rectangles, and therefore quadrigonal CATS is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CATS, side TS must be equal to the opposite side CA, but TS is 8, therefore the opposite side CA must be also equal to 8 units in its length. So if we found out that the length of the big rectangle EAFG is equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. That is the length of the rectangle. The width EF is 816, so the length times the width is the area of this rectangle EAFG. Repeat again. The area of rectangle, the big rectangle EAFG, that is the area that we are looking for this question, is equals to the width of the rectangle times the length. The width of this rectangle EFGA is EF, that is 16, times the length, that is EA. The length is 8. But again, the width is EF, the length is EA. So total area of the rectangle EAFG equals to EF times EA. EF is 16, and EA in total equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. So the area in total equals to 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. Square units in its size, so in terms of numbers, the value of this expression in total equals to 586.47 square units in its size. Okay, thank you very much.